Today we will start the very important part of chemistry. We know is organic chemistry, essential for you as then you will study one of the also very important subject, biochemistry, and you can't be successful there if you know nothing about the nature of substances, their structure, and that's why I can't predict their chemical and biochemical then behavior. So the first lecture is about structure, classification of bioorganic, please be attentive, bioorganic, not compounds, mechanisms of organic reactions, and if enough time, I will give you some information about acidity and basicity. So let us start. Bioorganic chemistry it's a branch of chemistry studying the structure and properties of substances participating in the vital functions. That's mean in a life process. All of them can be classified, no, we can say that not exactly classified, but main objects we're dealing with when we study bioorganic chemistry, biopolymers and bioregulators. Biopolymers, all high molecular weight compounds important for our biochemistry, peptides, proteins, carbohydrates, nucleic acids, DNA, RNA, lipids. Bioregulator substances that help the substance, previous biopolymers to participate in biochemistry. So vitamins, hormones, biologically active substances there. So what is organic chemistry? It's a chemistry of hydrocarbons and their derivatives. It's not correct to say that organic chemistry dealing with the carbon only, because of their huge number of inorganic compounds also consist carbon and can be even hydrogen in a structure. So, but more correct to say that hydrocarbons, saturated or unsaturated, doesn't matter. Hydrocarbons where hydrogen one or maybe few somehow substituted in exact group or one atom or group of atoms known as a functional groups. There are few classification, a lot of classification of organic compounds essential for us to know. Why? Because of them we will need these classifications, all of them somehow, to predict chemical behavior, and even we will need them to name properly. Naming of organic compounds, not all compounds important to name properly, but for organic it's essential because of number of organic compounds is really huge, much more than for inorganic. If some sources insist that inorganic compounds total number, all periodic table, give us less than 1 million, some sources 500,000, some bigger, but less than 1 million definitely. When we deal with organic compounds, their number of organic compounds for now more than 10 million and still rising because of new synthesis. So that's why classification here is really essential. Because of them only we can divide this huge number of compounds into smaller parts with similar properties, chemical, physical properties, rules they follow, and then we can understand why they follow these rules. So the first, the easiest classification, it's a classification according to the structure of carbon chain. Then I will tell you more exact. Second one, according to the nature of functional group. Very important. And according to the number of functional groups and their homogeneity. So the first classification, according to the structure of carbon chain. All organic compounds can be divided two parts. Aliphatic, that's mean non-cyclic. They can be branched, can be not branched, we know as a normal structure. So, but aliphatic and cyclic, where ring structures are present. So aliphatic, due to saturation degree, can be divided two parts. Saturated, we know the alkanes, and unsaturated, alkenes, alkynes, alkadines, that mean substances consist multiple bond, one or few. Saturated alkanes As example, ethane, and you should know the name of homological series of these substances. Methane, ethane, propane, till decane, you must know very good, because we will need this information then to name any compound we're interested in naming. Unsaturated, alkenes, alkynes, they have proper suffix, in for alkenes and ine for alkynes. Cyclic compounds themselves can be divided according to what atoms are forming the cycle. So homocyclic means that they are ring made by carbons only. Functional groups here can be present, but the ring itself made by carbons only. Heterocyclic compounds accept carbon in a ring supposed to be one or maybe few. Heteroatoms can be nitrogen, oxygen, sulfur mainly. So each one, homo and heterocyclic, themselves can be classified due to saturation degree. Alicyclic can be saturated, unsaturated. As example, take a look, cyclohexane, saturated compound, and it follows some chemical rules, same as alkanes do, but it's cyclic. There can be one, maybe two double bonds to be unsaturated alicyclic, but there are some separate list of substances which are aromatic. They follow different rules. Because of aromaticity, such compounds more stable, that's why less reactive, and even mechanism of reaction are different there. For them, typical different properties. So that's why it's so important to know is it aromatic or not. And I will teach you then how to prove it. Heterocyclics themselves also can be classified according to the saturation degree as alicyclic, saturated, unsaturated, and aromatic. Next, classification according to the nature of the functional group. What is functional group? It's one atom, maybe halogen or maybe oxygen, or group of atoms within a molecule that show the characteristic set of physical and chemical properties. According to the nature of functional group, our organic compounds can be classified in exact homological series, that means classes of organic compounds. And I will give you as example some of them, not all definitely, some as examples. Take a look. If there are no functional groups at all, such compounds are known as hydrocarbons. Again, according to the nature or according to the structure of the carbon chain, they can be classified as saturated, unsaturated, as aliphatic or cyclic, same classification as in the previous slide was given. But there are no functional groups. If there are hydroxyl present, such compounds, due to what carbon atom in a carbon chain it's bonded to, can be classified as alcohols, and according to the carbon chain structure, alcohols can be saturated, unsaturated, can be even cyclic. But if OH group bonded directly to the benzene ring Sp2 hybridized carbon atom, these compounds are known as phenols. It's a different class. So, carboxyl group, carboxylic acid. Amino group, amines. It's easy. And a lot of others. Functional group, oxo group can be there to be ketone or aldehyde, and so on. When we will name the compound, I will teach you again how they look like. According to the number and homogeneity of functional groups, our compounds, organic compounds, can be classified into three types: homofunctional or monofunctional. That means one functional group and that's it. For example, ethanol. Polyfunctional, when two and more functional groups present in the same molecule. For example, there can be diols or triols, like glycerol, for example. There are three OH groups. They have extra steps because of more functional group than one. They affect each other. And if their functional groups are different, such compounds are known as heterofunctional. And here, as example, you can take amino acids. Everyone knows structural units of our proteins. And biogenic For example, ethanolamine, some essential compound, amino alcohols group. So ethanolamine is a structural unit of such compound as lipids, and not only. Before to discuss chemical behavior and naming, I want to remind you why there are so many organic compounds, much bigger than inorganic, because of for them very, very, very much typical isomerism. What are isomers? A compound with the same general formula, same molecular formula, Bruta formula we say. That means number of atoms is same and nature of them is same, but there can be different structure to be constitutional or structural isomers. And their connectivity can be same, but same or not same, or different orientation of the atoms in a space, such known as stereoisomers. Each type of isomers can be classified into few. I will remind you just some, because of then we will study different classes and we will see what kind of isomerism typical for exacto. So isomers, it's the easiest classification. We can divide into constitutional or structural and stereoisomers. Constitutional themselves can be classified into chain isomers. For example, chain can be normal or can be branched. Positional isomers, that means here can be position of multiple bond. As we know, the double bond can be between first and second, between second and third, like for example pentene or pen2-ene. They are isomers, positional. Also can be position of functional group. It's the same positional isomerism. For example, it can be alcohols, primary, secondary nature. Functional group isomerism, that means it's isomerism of classes, like aldehydes and ketones. They are different classes with the same group, but they are functional group isomers. Here as example, enols, substances consist double bond NOH group bonded to the same carbon, and ketones, they are isomers, functional group, different classes, but same Bruta formula. Here can be also taken hydrocarbons, but they are no functional group at all, but they are different classes with the same Bruta formula. For example, alkenes and cycloalkanes. They are same general formula, but different classes follows different rules. Okay, stereoisomerism, different spatial arrangement, can be optical or known as enantiomerism, and geometrical, diastereoisomerism, more correct. Deeper, we will study this type of isomerism when we will start to understand properties of hydrocarbons and their derivatives. So that's why so many organic compounds, more than 10 million, as all inorganic, less than 1. They are also typical isomerism, but not so much. So, and now let us talk about naming. It's essential to know how to name an organic compound properly, as there are so many, and to understand each other if we live in different countries. To understand each other, we should choose the one way to name. Finally, what should we get? We need, if there are one name, there's supposed to be only one possible structure. If there are for name possible to draw few, that means you didn't name it properly. So, and there are here a few different types of naming. Can be common name. When we deal with such, we should understand that common names, like for example glycerol, like glucose, they give us no information about structure, and that's why different countries we can not understand each other because of such names. We should only memorize. Some at least sounds different, like glycerol and glycerin. But if we deal with carboxylic acid, Formic acid in English, it's a common, but it's a mуравьиная кислота in Russian, and we will not understand each other. So that's why here much more acceptable to use international system, we know is IUPAC, and there are also few types, and the most famous among IUPAC systems is the one I will explain you now. So name of any organic compound consists at least two parts. It's a word root and primary suffix. These two present always. Doesn't matter what compound we're going to name. Prefixes present only if their substituents are present. And secondary suffix if their functional group is. So what is prefix? Alkyl groups, methyl, ethyl, propyl for branched cycles. And some functional groups also should be mentioned among prefix. Not the main, and there are some list of functional groups always named as a prefixes. Word root. What is this? It's a parent chain. Or cyclic structure is a parent chain. What is here important? Parent chain and just the longest chain, it's not the same thing, can be. So it's very important to find the parent chain to find the proper word root. Primary suffix. Primary suffix depends on nature of the multiple bond. It's a saturation, or more correct to say unsaturation. So if they are only single bonded carbons, they are ane in our parent chain. It's an ane suffix. Double bond in, triple bond ein. And secondary suffix, I told you, only if they are functional group, the main one, nature, it's should be named among secondary. That means secondary suffix. So let us understand how to name secondary suffixes. So here the list of functional groups which are always named with the alkyl groups as a prefixes. They never in a priority list for suffixes secondary nature. So here nitro group, ether groups, alkoxy, methoxy, propoxy, butoxy, chlorobromo, iodofluoro. That means halogens also should be named here. They never form the secondary suffix. And here I will give you examples, here list of functional groups much bigger definitely, and that's why if we will going to name some organic compounds, sometimes we need to use more sources. But here the main functional groups we're interested in this cycle of organic chemistry. So the one is the most in priority order, the highest one, it's a carboxy group. So in here two possible cases. The carbon in carboxy group can be part of the parent chain. That means it will be numbered in a parent chain. It's indicated here with the color. It's always the highest functional group in priority order, and that's why it has only secondary suffix. I'm sorry. Can be situation carboxylic group not bonded directly to the parent chain, but through, for example, parent chain in cyclic structure, it's a cycle. And that's why if there are cyclohexane and carboxylic bond group bonded to it, the carboxylic group will be not numbered, the carbon in carboxylic group, but the carbon in a cycle which is bonded to the carboxy group is number one. So in such case, OX suffix can't be used. They are different suffix, carbonic acid, cyclohexane, carbonic acid. But if there are two, both of them present in the same formula, the one which is part of the parent chain and the one which is not, the one is not, the second one, carboxy group, becomes as a prefix present, carboxy as a prefix, and the first one gives us OX suffix. They are both prefix and secondary suffix in one name. Low in priority order, sulfonic acid functional group. It's a sulfur group if it's combined with a higher one. That means carboxy group in the same formula. That's mean for heterofunctional compound. And if it's only one or the heterofunctional with some functional groups lower in this priority list, it's sulfonic acid. Then what? Oxo group can be aldehyde or ketone. Aldehyde group higher in priority order. So that's why if they are both present, an aldehyde and keto group, there will be al suffix but oxo prefix. Prefix is same here. Hydroxy group, alcohols, mercapta groups, thiols. So that's mean if they are only SH, it's forming the secondary suffix. But if there will be combined, for example, with carboxylic, it's mercapta prefix. And the last one, the lowest here in priority order, it's amino group. In this table, can be more. Amino. So be attentive, amino group as a prefix, but amine as a secondary suffix. If it's the highest in priority or the single functional group present. And also one information, so very important for you to understand. Priority order important for naming. It will not affect the reactive ability, reactivity of this functional group. Amino group can be much more reactive in some reaction than carboxylic, being low in priority order. And now let us understand how to name, what rules we should follow. First one, to name the organic compound, anyone, we need to number the parent chain. But to find the parent chain, we need to follow some steps. First of all, we should find the functional group. Do we have it there or not? And if there are few, if it's heterofunctional, using priority order, we should find the highest one. After this done, we should select the parent structure. It's the longest continuous chain containing the highest number of functional groups, the highest number of carbon-carbon multiple bonds, double, triple, and if there are same number of previous, or there are no functional groups or no multiple bonds at all, we choose the chain among those longer, the highest number of substituents. So better few small than one big substituent with the same number of carbon in a parent chain. So after this parent chain is found, we need to number this chain properly. Because of position of substituents and even suffixes is essential to name compound. So that's why numbering of carbon in parent chain, to number it properly, we should number such way. The highest functional groups in priority order should be numbered. We should choose the direction where this functional group, the smallest number can be. It doesn't mean that we should start with. Only if it's in the end of the aliphatic structure. It's important. So alcohols can be primary, secondary, tertiary. That's why they have the number of OH group. It's bonded to the, so it can be 2 ol, 3 ol, 5 ol. It doesn't mean that we should start numbering from. But we should number the carbon chain, the parent chain such way the functional group have the lowest possible number. If there are no functional group or it's an exact central part, doesn't matter from left to right we number, we need to choose the direction, the double, triple bond, the smallest number as possible. And after this done, if they are double, triple bond, also same number or it's absent, then we choose a direction. The substituents total number is smallest. That means it seems like they starts earlier. But again, priority order, the functional group first, then double, triple bond, and then prefixes. So after this done, after the parent chain is numbered, we are ready to name the compound. And definitely we should start with the prefixes in alphabetical order, not according to their appearance, but according to alphabet. Locants, that means carbon atom, this prefix group bonded to, must be named before the name of the group. 2-methyl, 3-ethyl, and so on. After prefixes are named, we need to name the root, the pairing chain. The number of carbon atoms in a pairing chain till 10th you should know very good, maybe better than you know your names. Meth, et, without suffix, meth, et, prop, but, pent, hex, hept, oct, non, dec. This you must know. After this done, we need to name the primary suffix with indication of the position of the multiple bonds if they are present. So in if it's single bonded, in or ein if it's double or triple bonded, with the position, with the location of this multiple bond if it's present there. And then we name the secondary suffix properly according to the table I just mentioned before. So now we know how, and if position of the secondary suffix group not in a first one usually we not indicate, but if it's second or third or further carbons bonded to, we need to indicate locants as well before the name of the functional group. So and let us practice now. So for example, let us take such heterofunctional compound. Why heterofunctional? There are two functional groups present, hydroxy group and carboxy group. So it's same, it's a hydroxy acid, unsaturated aliphatic, if we need to classify this compound. So what we should do to name this compound properly? We need to find the pairing chain. Again, to do this, we need to find functional groups. Do we have there? Yes, we do. There are two of them. That's why we need to choose the one which is the highest in priority list. The one which is the highest is a carboxy. That's why I marked this with a color. That's why OH group, now not the secondary suffix group, but the prefix group. And it will have the name hydroxy, but not all. So after it's done, and we know that secondary suffix is present, we need to find the pairing chain, and its longest among those consists the highest number of functional group, but the multiple bond as well. That's why it can be not the longest possible. Take a look, the longest, it's 8 carbons. 1, 2, 3, 4, 5, and 3 more. It's 8, but it's not a pairing chain. The pairing chain will be 1 carbon shorter, 7, because of the one consists 8 carbons, not consists double bond. It's unacceptable for the pairing chain. So that's why we will choose the longest from those consist our functional groups and the multiple bonds in one. No, it's a normal structure chain, straight one. After this done, we need to number properly before to name. And again, we number such way our highest functional group has the smallest number can be. So that's why here we will number it from right to left. But if there are no functional groups, we will prefer the direction the multiple bond has the smallest number as possible. So let us number. The numbers we indicate, the carbon numbers, we indicate above carbon atom. Because of below, we indicate number of atoms. So that's why it's important to write properly. So it's numbered. Then we're ready to name. What we do? We name prefixes first, alphabetical order. Let us check how many prefixes here. We have 3. 3 outside the pairing chain. Pairing chain, each one carbon which is numbered, they are present in a name of the pairing chain, not in a prefix. So now alphabetical order, we need to name them. This is methyl, this is propyl, normal one, not iso because of the 3H7 mentioned, and hydroxy group. Which one first? Hydroxy definitely. We indicate the position, the carbon number of the carbon is bonded to 3 hydroxy. Then M according to alphabet, 6 methyl, then propyl, and then we need to name the pairing chain. Hept. No suffix yet. If there will be saturated one, alkane will be heptane, and that's it. But now we see that double bond, it's not between first and second, and it has name in. That's why first of all we need to indicate where is it. It's fifth position, in. If that's it, ENE we write, but here then we have oic acid. So that's why E is cancelled. Enoic acid. Two words. Because of acid, it's a second word. But this one, it's a one long. In some sources, we ignore dash here between the previous and further prefix. But mainly we use prefixes to separate parts of the name from each other. But it's one word. One word. What about cyclic compound? This one, cyclic, alicyclic unsaturated compound, we need to name. So I already numbered properly. For you to understand how to do this, what we should do to name such compound? Again, here no functional group, that means no secondary suffix. Parent chain is found already, it's a cycle, it's a ring. That's why our problem just to number it properly. What way? As no functional group, that's why we need to number such way our double bond as smaller number as possible. So that's why we can start 1, 2 here and follow anti-clock, or we can start 1, 2 opposite direction and follow clockwise. Now, if it's same, we need to choose the direction. Our substituents starts earlier, that means it has the smallest number. So if we will move according to what I did, the first substituent first position. If we will number other way, the first substituent will be second position. That's why definitely we will prefer anti-clockwise. Okay, now we should name our substituents as a prefixes, alphabetical order. Here, as you see, we have ethyl. It should be named first. So 3-ethyl. And then we have, as you see, few same nature substituent. Methyl, there's 3 of them. Each one bonded with a covalent bond to exact numbered carbon. That's why 3 different groups bonded to the parent chain. That's why 3 numbers. Doesn't matter, it's same. They bonded each one with their own covalent bond, not through each other. Like ATP, then we will study such compound. There will be 5th present ones. Adenosine triphosphate. Adenosine 5 once mentioned. Why? Because of their triphosphate bonded ones are not 3 different phosphate groups. Here, methyl groups, each one bonded. So that's why 1, 5, 5, trimethyl. Prefixes dia, tria, tetra, penta, and so on. Same as in coordinational compounds. The naming you know already quite well, I hope. So after the prefixes are named, we should name the parent chain. Here it's a ring structure, so that's why it will be cyclohex, not hex just. Be attentive when you name such compounds. Cyclohex, it's not aromatic to be benzene. There's supposed to be alternate position double single bonds in it. So this is unsaturated alicyclic compound. Cyclohex, then we need to indicate suffix, primary suffix, it's a in. But usually we never indicate first position. That's why if it's mentioned cyclohexene, just be sure it's a first. So this is what I want to remind you about naming. Now let us talk about structure of organic compound. And to understand how this compound behaves, then we need to know types of bonding. No, and I will remind you how carbons themselves looks like to be bonded exact way. So there are 3 main types of chemical bonds can be found in organic compounds. The main one, covalent, it's present always. But in some compounds like carboxylic acid salts, like secondary, tertiary structure of the quaternary structure of proteins, can be present ionic bond. Hydrogen bonds also important. It's not often present, but it's changed everything. It changed stability. It's for example, hydrogen bonds stabilize secondary, tertiary, and even quaternary structures of proteins. They stabilize double helix in DNA, and also cloverleaf if we deal with RNA. They're essential for chemical behavior of alcohols. So that's why hydrogen bond, being very weak one, still it's very important, but not the main. Covalent bond, which happen as a result of overlapping of orbitals, it's present always. So as a result of covalent bonds, as a result of overlapping, there are two electrons between two centers formed. Mechanism not important. Here can be which each one can share for the covalent bond formation one orbital with one electron on it, or the donor-acceptor mechanism can be. As a result, it's the same lone, same energy bond, but overlapping can be different. Overlapping, sorry. So what is here I want to tell you? Here we have, to understand kind of overlapping happen there, I want to remind you electron configuration of the carbon. So normal structure in periodic table, you can find the number of electrons there. So what here we can see that when carbon participates in the formation of the compound in a bonding, it becomes excited. So, and due to this, one electron from 2s orbital from normal structure shifts to the pz orbital, slightly higher level. So definitely takes a little energy, but then it compensates when the bond is formed. So what here we see, the first level not participate in the formation of the bond, but second one is. And due to the nature of the bond, these orbitals takes part in formation. There are different hybridization appears. What is hybridization? Hybridization, it's a combination, mixture of orbitals, two or more, with formation of new, according to the shape, atomic orbitals. We call them hybrid orbitals, but they are same number of hybrid orbitals formed due to the result of mixing of non-hybrid orbitals. There are three types of hybridization typical for carbon atom: sp3, sp2, and sp, according to their what orbitals and how many of them hybridized, mixed with the energy. So I just want to remind you, this is school level. You must know how hybrid orbitals look like, and valence angle you should know as well. So to understand the nature of the covalent bond, then I will remind you hybridization. Covalent bond can be as a result of sigma, that's mean direct overlapping, and here can be non-hybrid or hybrid orbitals overlapping. Can be pi bond. Pi bond, it's a side overlapping, formation of unsaturated compounds, multiple bond, weaker definitely according to the energy, if to combine with a sigma bonding. So that's mean in a compound they're supposed to be hybrid or non-hybrid orbital for side overlapping. So sp3 hybridization, they are all second level orbitals mixed with the energy and its shape. So 1s and 3p orbitals, all of them formed 4 hybrid orbitals, same shape, same energy, and that's why their orbital is an electron cloud. They are trying to be as far from each other as possible, forming same angle, 109.5, some sources 109.25 hybrid orbitals, and that's why they're only direct overlapping possible. There are no unhybrid, that's why only sigma bonds can be formed. And I want to remind you that such type of hybridization possible not only for carbon atom, but for other like nitrogen, oxygen, can be, there are 1 or 2 electrons number higher than for carbon, and that's why there will be hybrid orbitals with a chance to donate lone pair. Sp2 hybridization. In this hybridization, just one s and two p orbitals takes part with the formation 3 hybrid orbitals, same shape and same energy, but one pz orbital staying to be unhybridized. It's staying same as it was, right angle to the hybrid triangle. So 3 hybrid orbitals forming triangle plate, 120 angle between them, and that's why it's only one hybridization to form something plate structure. That's why it will be important to find is our carbon sp2 hybridized or not when we will prove aromaticity. And unhybrid, it was right angle to other p orbitals, and it's still right angle to these triangle hybrid orbitals. So how this looks like when formation of the bond appears. So double bond, 1 pi bond appears in alkenes, realized there. So for example, ethene, they are 1 sigma, 1 pi bond. Sigma bond formed as a result of direct overlapping together, same as the hydrogens here, and unhybrid pz participate in the side overlapping. It's a 1 pi bond, doesn't matter above and below, it's same orbital, side overlapping. So about sp, shorter information, they are 1s, 1p orbital. That's why two same hybrid orbitals formed linear. It's a 180 angle. That's why two pz and py orbitals stay right angle to each other and to this hybrid orbitals line. So that's why our ethyne, as example, they are 1 sigma direct overlapping and 2 side overlapping, 2 pi bonds. As a result of all this, even for pi bond being weaker than sigma, the distance between atoms when we deal with a double or triple bond becomes shorter for side overlapping happen. So carbon-carbon, it's just information for the most common compounds because of presence of some functional groups can affect the longest of the carbon-carbon bond. So just a typical case, carbon-carbon single, it's 0.154 nanometer. Double shorter as a result of side overlapping extra, 0.134. Nano, I want to remind you, it's 10 power negative 9. And triple bond much shorter, 0.12 nanometers. The bond energy means energy needs to destroy all of this. The carbon-carbon bond doesn't matter, single, double, triple, not one of the pi bond. So that's why bond energy rising with a number of extra overlappings. So that's why triple bond to destroy all, we need say more than 2 times higher value of energy, kilojoule per mole. And very important, there are more characteristics of covalent bond, but now I will mention just 3 of them to understand then factors affecting. So very important factor, polarity and polarization. So what is polarity? So according to the structure presence of different atoms or functional groups, set of atoms, compounds can be polar, can be not. For example, alkanes, they are saturated hydrocarbons, they are non-polar at all, and they are only same hybridization, carbon atoms present. So carbons and hydrogen, we say almost same electronegativity. Electronegativity, as you remember, rising from left to right in a group, in a period, and a group it's rising from lowest to up. So that's mean, as you remember, I hope, the highest in electronegativity, it's a fluorine in the periodic table. So that's why if there are different electronegativity present, it attracts electron density or can push. So more electronegative attracts electron density, polarizing the carbon chain, polarizing the bond. And as a result, there are different properties. Non-polar, for example, they are insoluble in water because of like dissolves like, as you remember. Polar compounds, they can be soluble in, and they follow different rules. Sometimes it affects selectivity of the chemical reaction. So polarization, it's effect of the presence of exact nature groups. There can be sigma bond polarized, is known as inductive effect. It's a displacement of electrons along a carbon chain, sigma bonds. So these bonds, they are fixed between two carbons as they are formed as a result of direct overlapping. So that's why inductive effect decreasing with the distance. The highest one between first and second carbons, and then it becomes smaller, and after third carbon, that means fourth, after fifth bond, it's already, we say, no effect. Inductive can be positive, negative, then you will see what is example. And can be mesomeric or resonance effect. Mesomeric, present not always. If inductive effect, present always if we deal with a different electronegativity atoms in the same molecule. Mesomeric, present not always, and it's a polarization of the pi bond. In unsaturated compound, it will be not realized. And also for displacement of the pi bond, the group going to affect it should participate in a delocalization. It should take part in a formation of the extra overlapping. So that means the group itself should be in proper direction, and it should be able to form the pi bond. For example, alkyl groups, methyl, ethyl, they can't, but of course mesomeric effect if they are all carbons sp3 hybridized. So let us see how it's look like. So inductive and both mesomeric as well, they can be positive or negative. That means they can be donating and acceptor groups. So what is positive inductive? So to understand electron negativity, I told you should use information from periodic table. And here what's important, then I will mention acidity, basicity, and you should understand. Carbon seems like same electronegativity, but it's a little but different due to hybridization. sp3 hybridized from all carbons, more electropositive. They are very small difference, but it's a little but small, more electropositive. sp2 a little more electronegative, and the most electronegative from carbons, the one which is sp hybridized. So that's why when in a hydrocarbon here, they are both present, different, sp3 for example and sp2, the one more electropositive, sharing electron density. It seems like it's pushing, but between carbon they're covalent bond. It can't be shifted somewhere. It's still, as a result of this effect, what's happened? Electrons of this overlapping becomes closer to the second carbon here. That's why, as a result, electrons closer here, and as a result, next bond also polarized. That means finally the last one carbon here, but if we go into number, it will be first, as we will number from right to left. But this carbon, this according to the appearance here, it's third, become minus delta. It's appears the charge very small minus, but it appears there. So as a result of positive inductive effect of methyl group. For negative inductive effect, there's supposed to be present atom or group of atom with a higher electronegativity than carbon. So what is here? We're talking about effect of the group on the parent chain, the carbon chain, not what's happening inside the group itself. So what do we have here? Oxygen as a more electronegative, attract electron density from the parent chain, from the carbon it bonded to, and that's why it caused polarization of the further. But this one, the first one between oxygen and the carbon, the biggest polarization. next one weaker, then weaker, and fifth one we accept and nothing already happened. So as you see, the bond itself becomes zero. We never drew in any extra arrows when we indicate inductive effect. For mesomeric, as the overlapping for pi bond happen above and below, that means not in the line between atoms. So there we add extra curved arrows showing where pi bond closer to each atom. So for example here, for amino group, negative inductive present. So we will draw here arrow directing from carbon in a benzene ring to the nitrogen. But also nitrogen, it's a source of pz electron pair, alternate position to the sp2 hybridized carbon in benzene ring. Here extra overlapping happen is at alternate position, and excess of electrons, this nitrogen sharing with a benzene ring. So electrons moving in the delocalized pi bond in benzene ring, and that's why each pi bond here becomes polarized. So this pi bond, the closest to the amino group bonded carbon, polarize, and that's why here carbon, the second one, become minus delta charged. It causes polarization of the next alternate position pi bond, and as a result we see that exact numbered carbon become minus delta. It's a result of a direction. Amino group is ortho para director group. Then I will explain this again. So, but the reason is positive mesomeric effect of our amino group. Negative mesomeric effect happen if the group itself can't be source of electrons at all. For example, groups where oxygen present bonded to the atom, which then will be bonded to the parent chain. In this oxygen cause polarization inside the parent chain, inside the functional groups, I'm sorry. So as you see here in aldehyde group, oxygen already itself attracts electron density of the pi bond and cause a carbon atom in this oxo group becomes plus delta. It can't be source of electron density in any cases. Negative inductive also, but negative mesomeric as well. It's attract electron density, same direction, and cause that pi bond here, second position carbon minus delta, the last one plus delta. That's why if then we will see addition to the unsaturated aldehydes, you will understand why here addition will happen anti-Markovnikov's rule. So as a result of summation of these electron effects, inductive and mesomeric, they can be both present, and one of them can be bigger or smaller. As a final electron effect of the functional group, how it will affect our parent chain, we will get the next picture. So alkyl groups, methyl, ethyl, propyl, butyl, they can't cause mesomeric effect ever, and there we have no chance for side overlapping there. Sp2 hybridized, they are not present, they are Sp3 hybridized. So that's why only positive inductive, that's why they are donating group, always. When we deal with such group as amino group, primary, secondary, tertiary, doesn't matter, or alcohol group, or ether group, or Mercaptor group, they are everywhere. In all of these cases, nitrogen, oxygen, or sulfur is a source of lone pair, 2 electrons on each. That's why being negative inductive group, because of more electronegative atom than carbon in each case, they are positive mesomeric effect. Here, positive mesomeric is almost always bigger than negative inductive. That's why resulting, they are donor group. If their both are present, mesomeric higher, and that's why they are donors. If there will be unsaturated, for example, alcohol like pentanol, there will be only negative inductive and it will be accepted definitely. But if they are both present, it's a donor group. Halogens situation is different. Why? Because of negative inductive as more electronegative, positive mesomeric, they are lone pair present, but they are the most electronegative atoms can be. So that's why for them electronegativity results in negative inductive more than positive mesomeric, and halogens are acceptors. And there are some list of groups, same as oxo group I mentioned just a minute ago. Inside the group already polarization happened. Oxygen in each group attract electron density, leaving behind in oxo group carbon plus delta charged, in carboxy group plus delta charged carbon, here eta also carbon plus delta, here nitrogen plus delta, and sulfur plus delta charged. As a result, they can't be donor anyway. They can't cause displacement to the carbon chain. They attract electron density both negative and inductive, and if they participate in extra overlapping, there will be negative mesomeric also. Doesn't matter which one bigger, they are acceptor groups always. So what is conjugation? I mentioned already a few times. Conjugation is a result of extra overlapping of unhybridized pi orbitals with the formation of delocalized pi bond. It's an extra overlapping. This is important to understand. So conjugation, according to the what extra overlapping happened, can be two types. It can be pi-pi conjugation if their overlapping happen for alternate double, single, double position, double bonds, and doesn't matter is it double bonded carbon or oxygen, so alternate position, double, single, double. Or it can be p-pi conjugation if the pi bond of the double bond conjugation extra overlapped with a lone pair donor alternate position to it. So pi-pi conjugation, take a look. The classic benzene and but-1,3-diene. Double, single, double, doesn't matter ring structure or aliphatic. Extra overlapping with the formation of delocalized pi bond. And unsaturated aldehyde, it's acrolein or propanol. So here double, single, double, doesn't matter oxygen there. Delocalization happen, here formation of such delocalized pi bond as a result of pi-pi conjugation. For p-pi conjugation, it also can happen in aliphatic structure or cyclic ring structure, supposed to be lone pair donor alternate position. So here pz orbital present, and that's why extra overlapping happen with a pi sp2 hybridized carbon bonded double bond. And here also double, single, double pz orbital with a lone pair. This is p-pi conjugation. As a result, they are delocalized pi bond present. So, and that's why here now we can use this information to understand nature of some compounds, unique nature compound, where aromaticity appears, aromaticity realized. As I told you already, then aromaticity, presence of the localized pi bond in a ring structure, conjugation itself stabilizes structure. Formation of the localized pi bond, it happens spontaneous. So that's why no extra source of energy needs. It happens spontaneous because of its stabilizing, it's lowering the energy. So that's why aromaticity. So if compound is aromatic, it's less reactive. And not typical additional reaction for such compounds, but more substitutional reaction, much more typical for. So that's why some compounds, they look like aromatic, but they are not. And that's why they will follow different rules. They will follow unsaturated ring structure rules. So that's why we need to know how. There one rule, really one, it's Haeckel's rule, but it's consists few parts. We need to be sure that they are correct. So for compound to be aromatic, it should be coplanar cyclic with a delocalized pi bond, all atoms participate in formation, and the number of electrons in this delocalized pi bond supposed to, according formula for n plus 2, it's a Haeckel's formula, give us integer n. So that's why I say the lone one. That's why, to prove aromatic or not, let us cut this lone sentence into 3 parts to prove. The first one, it should be coplanar cyclic. To be sure it's coplanar, we need to check, are they all carbons sp2 hybridized or not? And one more thing we need to check, not mentioned here, and I don't know why not mentioned almost in any book. The total number of atoms in a ring supposed to be sp2 hybridized from 5 to 7, not less, not more. Because of sp2 hybridized atoms, their valence angle 120. If there will be less than 5 and more than 7, it will be stressful situation and their conformation appears. Aromaticity will be destroyed in such case. That's why we need to check not only sp2 hybridization for atoms, but we need to calculate how many of them there. From 5 to 7. Second, it's a presence of pi electronic system, conjugate 1, all atoms participate in formation. So that's why it can be here p pi or pi, doesn't matter, but they are supposed to be formed delocalized pi bond. That's why alternate position or double bond supposed to be, or double with a pz lone pair donor atoms, like p pi conjugation. And the last one, Haeckel's formula for n plus 2, we need to calculate how many electrons in delocalized and conjugated system, delocalized pi bond, and find the n, which is supposed to be integer. So, as example, let us take homo and heterocyclic compound, benzene and pyrrole, both important. So what should we check first? First, we need to check is it coplanar cyclic or not. So let us see in benzene. All carbons sp2 and total number of atoms 6. It follows, that's why it's coplanar cyclic. For our pyrrole, it's same situation. All carbons sp2 and total number of atoms 5. So that's why it's coplanar cyclic. Second one, we need to check is there present delocalized pi bond, all atoms participates in. So take a look, alternate position, double single bond. That's why pi conjugation they are realized. For pyrrole, alternate position, double, single, and lone pair donor. That's why total conjugation is p-pi conjugation. Conjugation here can be present but be not all atoms participate in formation. Partial conjugation, unacceptable for aromaticity rules. If there are at least one carbon atom, sp3 hybridized in the cyclic structure, we will write there no conjugation, means that not all atoms participate in formation of this delocalized pi bond. We need the ring, not half moon for aromaticity. And the third one, Haeckel formula for n plus 2. Every double bond, it's a source of 2 electrons for side overlapping, and lone pair donor, it's clear 2 electrons source. So Haeckel's rule for benzene for n plus 2 is 6, as there are 3 double bonds, and for pyrrole, it's also 6, and n equal to 1. Both compounds are aromatic. So I hope it's clear, and that's why they will be discussed at different day, because of they follow different rules. So what then important to understand? To understand the mechanisms of chemical reaction, what's happened inside the chemical reaction, we need to understand what's happened with the substances due to bond fission. So there are 2 types of bond fission. It's a homolytic and heterolytic. Homolytic fission happens as a result of some effects like heat, like UV light, and as a result of such type of fission, their radicals are formed. quite reactive particles. That's why radical reaction usually happen with fast rate, even explosion quite often. Heterolytic fission causes formation of two particles charged positive and negative. The more electronegative element usually attract electron density completely, and seems like becomes ionic. So what here happen? One positive charged will attract to the electron, that's mean negatively charged part in substrate, in our initial substance. So that's why it's known as electrophile. And the one which is negatively charged likes nuclear, that's why nucleophile. So due to what is the factors cause bond fission? Same substance, same molecule, for example, halogen, chlorine or bromine, can participate in homolytical or heterolytical fission. So reagents as results of this fission can be radicals, electrophilic reagents, and nucleophilic reagents. So electrophilic reagents, it's a proton, methyl group can be, and some neutral where element which is participate then in electrophilic reaction positively, partially positive charge as a result of polarization already happen inside. Oxygen already cause sulfur, they are almost same electronegativity, but oxygen a little bit more, they are same group elements. Nucleophilic reagents, negatively charged particles or molecules with lone pair donating group like ammonia, nitrogen lone pair donating group. Water can be here, but water can be electrophilic and nucleophilic both due to what reaction it participates in. So types of reaction due to what's happened with the initial substrate. There can be substitutional, easier to say. There were two reactants and two products still. Additional reaction, A symbol, that means there were few reactants becomes one product. Elimination from one reactant, few products. Rearrangement, one was one still but with a different structure. Now in the oxidation reduction we discuss there are different types of reaction. There can be mixed of few mechanisms. So that's why now we can get types of organic reactions according to the mechanism of reaction. The most typicals are mentioned here. No elimination, I told you, rearrangement, they are different, but what reactions typical for main classes? So alkanes, because of their non-polar, and that's why nucleophilic, electrophilic reaction, they are impossible to get. For them, typical only radical, free radical. Again, the most typical means, it doesn't mean that other can't. Elimination can be here. But the most typical easy happen with a higher percentage of product. It's a free radical substitutional reaction. Or just SR. So unsaturated compounds, hydrocarbons, unsaturated compounds with no functional groups present there. That's mean double, triple bonded some. For them, as their pi bond present, additional reactions are typical, as pi bond much easier to destroy than sigma bond. Why electrophilic? Because of double and triple bond, as a result of extra overlapping, they are, it seems like, between two atoms, the high electron density. Take a look, single bond, normal electron density, there are just 2 electrons between two centers. But when we deal with the double bond, there are 4 electrons. Triple bond, 6 electrons. That's why they will attract, the bond itself will attract positively charged particles. That's why the mechanism electrophilic addition, the most typical. It doesn't mean that substitutional reaction can't be there. If we will find proper condition, we will get it. Aromatic arenes, so they are as aromaticity, increased stability. That's why additional reaction here not typical. It doesn't mean that they can't happen. They can, but they are not typical. The most typical reaction, substitutional nature. Why? Because of they will not affect aromaticity. It still will be there. one or few hydrogens in a ring can be substituted into some other groups. And because of benzene ring, it's a 6 electrons delocalized. It's a high electron density. That's why, due to these reactions, positively charged particles attract to this benzene ring according to the mechanism steps. And as a result, mechanism electrophilic substitution. For aldehydes and ketones, for oxo compounds, a double bond is present, but it's a bond between carbon and oxygen, which is polarized already, and that's why carbon there, which is bonded to the parent chain, which is part of the parent chain, is plus delta charged, and that's why their nucleophilic reaction will be possible and typical and additional because of unsaturated situation. For alcohols and carboxylic acids, substitutional reaction typical because of in alcohol there are no double bond and OH group. In carboxylic group the double bond not so easy to find because of their delocalized bond. Carboxylic group they are carbon double bond but carbon OH group bonded. They are p-pi conjugation and the pi bond delocalized, and that's why carbon in a carboxyl group it's a plus delta charged to be result of nucleophilic reaction, but substitutional reaction more typical. So other can be for carboxylic, even decarboxylation reaction can be loss of CO2, but SN mechanism reaction much more typical. So just a few words information about mechanisms of chemical reaction. The most typical, I just want to remind you. So what are radical substitutional reaction? As example, alkanes, the most typical for them. Again, for homolytical fission, it can be temperature, can be UV light, the most often. So methane with a chlorine, Cl2, CH4 plus Cl2. With the help of light, there one hydrogen substitute in the chlorine and we get chloromethane, and HCl is the second product. The mechanism, substitutional radical mechanism, there are 3 steps of this mechanism. First of all, for radical reaction there's supposed to be chain initiation, formation of the radical as a result of homolytical fission. So chlorine molecule absorb this quantum of light and form absolutely safe 2 radical. One of them will start the long and very fast chain reaction. The second step is known as chain propagation. It's the main one, chain. So the chlorine radical formed due to initiation step attack our substrate and cause homolytical fission of the bond between carbon and hydrogen. As a result, their new radical appears, methyl radical, and HCl as a second product. The new one radical, methyl radical, now react with a chlorine molecule to cause the final product, chloromethane, and the chlorine radical, which is attacked next methane molecule, and so on, so on, so on. What is important here? Summation of chain propagation step should give us the initial chemical reaction, and they are the main steps cause formation of the product. Take a look. If we will sum these 2 reactions, we will cancel chlorine radical and methyl radical. As a result, we will get methane with chlorine forming chloromethane and HCl. If we see it's true, that means our chain propagation steps are written properly. But they are, because of this reaction is very, very fast and non-selective mostly, so radicals can find each other due to this reaction. So in same reaction mixture they can meet each other. If it's happened, there are no more radicals left, and it's a way to stop this process. So chain termination, no more radical reaction. So as there are 2 radicals there were, halogen and methyl, so that's why 3 possible cases. Chlorine with chlorine forming initial chlorine molecule, chlorine radical with methyl radical chloromethane, and the chance to find each other for alkyl radical much smaller. That's why percentage of ethane will be very small, but it will be found. as more branched the initial substrate, as less chance for alkyl radicals to find each other. So what about chain reactions we should know? Radical reaction depends on size of radical. This is one important thing. There are no charges. Radical, it's a electron, one electron, unpaired electron source particles. So that's why only one factor will affect the chemical reaction rate and selectivity. It's the size of the radical. As small as the size, as more reactive the radical, as faster the rate of chemical reaction. If we will take halogen as a source of information about size, so we know in a group size is rising. That's why fluorine, the smallest radius, the smallest size in this group. Chlorine slightly bigger but still small. Bromine bigger, the biggest one among them it's iodine. So as a radical. So that's why here it's important to understand. If reaction happen too fast in a radical case, there are no chance to find the weaker bonded hydrogen. Reaction happen non-selective way as it too fast. That's why percentage of primary substitution will be bigger just because of primary hydrogen numbers is the biggest. Here in this 2-methyl-butane formula, we have 9 hydrogens primary nature and they are bonded to the primary carbons. I want to remind you that primary carbon is a carbon which is bonded once to other carbons. So here 2 secondary hydrogens because of they are bonded to the secondary carbon, and just 1 primary. 9 to 2 to 1. That's why chance to find primary much more bigger, as you see, than to find secondary, and small chance to substitute primary. We will get a mixture with a priority for primary one. So, but what will happen if there bromine as a radical present? Bromine radical also reaction is fast, but it's a smaller rate than for chlorine. For fluorine, such reaction we never even discuss. Why? Because of fluorine too fast that it can even destroy carbon-carbon bond, cause homolytical fission of it and the bond, and that's why it's a mixture of product they are formed. It's terrible mixture of product. So what is here with a bromine? As bromine radical smaller or bigger in the size, smaller rate, slower rate, it has, we can say, enough time to move to the weakest bonded hydrogen to cause homolytical fission, in our case tertiary, and not 90 because of inorganic chemistry, almost never 100%, but more than 90% of the 2-bromo 2-methyl-butane. More than 90%. That's why we can even ignore the chance of primary and secondary hydrogen substitution. Reaction happen selective way. Same will happen for nitration reaction. Nitration of alkanes happen as a result of reaction with a diluted nitric acid. For radical reaction here we need temperature, not a light, and then nitroalkanes are formed. Also selective way as NO2 radical, bigger size even than bromine. What about additional electrophilic? Additional electrophilic reaction happened as a result of heterolytical fission, and its substrate should be unsaturated, double, triple bonded. So what we have here, and it doesn't matter, it can be aliphatic or cyclic, but unsaturated, not aromatic, unsaturated. So the example here given, it's a test reaction on the double bond. It's a reaction with bromine water. We need no catalyst here, it's happened itself. When our double bonded substance, for example, a thing, pass through the bromine, even bromine water. So as a result of this reaction, we have 1,2-dibromethane. And how this happened? Additional electrophilic mechanism. It includes few steps, one from each other, with a formation of intermediate. Please be attentive, not activated complex, but intermediate substances. They are present, can be fixed. In some cases, it can be even stopped in a presence, in a formation of some intermediate. So first of all, bromine itself, it's not a charged particle. So why here additional electrophilic? Because of when we mix these two 1-to-1, when these two substances, ethene and bromine, become close to each other, because of presence of the higher density double bond, the bromine molecule is polarized. Ethene causes polarization of bromine. The part of bromine closer to the double bond is plus delta charged, and the second bromine minus delta charged. As closer to double bond, as more polar the bromine bond, bromine covalent bond, and this one, it's a pi complex. The way to show the pi complex, what is the plus delta bromine attract to the pi bond, not to the sigma, to the pi bond. It's like in contact with. There are no bond yet. It's just a complex with no bond destroyed yet, no bond formed yet. So, and again, because of this attraction of the plus delta to the pi bond, second, the bond bromine bond becomes ionic finally. So, and bromine minus leaving the formula. So, but staying close enough because of their bromonium ion is formed. Bromine on a pi bond, it's contact with a pi bond forming bromonium ion. So it's unstable situation, very short life situation because of pi bond belongs to 3 atoms. It's absolutely unstable situation. And very fast bromine choose one of the carbon. Here they are both absolutely same. That's why it's this carb cation can be plus carbon right side or left side, and second one bonded to the bromine, sigma bond. As bromine minus charged was somewhere around, when carb cation is formed, it's attracted to it to form covalent bond. Usually it's a transposition situation, but here to name just. So this is 1,2-diabromo ethane. Non-selective situation, but if there will be polarization in initial alkene formula, the addition can happen selective way. Everyone knows Markovnikov's rule, Russian scientist. Rule propene, for example, where present inductive effect inside, this formula is polar. Polarized, more correct to say. Why it's polarized? Positive inductive effect. That means methane group pushing electrons in the direction of the second carbon. And then, as a result of this, carbon trying to compensate this excess of electron, pushing its further K to further carbon. And as a result, the last one, according to numbering, it's the first one, minus delta charged, and the central one, it's a plus delta charged. So what is here? HBr plus delta charged hydrogen minus delta charged bromine. Hydrogen adds to the more hydrogenated, bromine to the less hydrogenated. This is Markovnikov's rule. Rich get richer. Proton of an acid adds to the carbon. An acid can be water also, their proton. It adds a double bond, which is already carbon, already the most hydrogenated. So that's why it's a selectivity, because of inductive effect. Please, that's why to know inductive and mesomeric effect is so important, as then mesomeric effect will be result of ortho-meta-para position. So, 2-bromopropane. What about cycloalkanes? It's a few more words. So what about cycloalkanes? They are saturated compounds, saturated. They are all carbons sp3 hybridized, but the unique situation with cyclic structures here as a stressful can be. So cyclopropane we know is a small cycles, cyclopropane. Take a look. Supposed to be angle 109.5. But as a result of structure, it's stressed almost 50. Why? Because of they are supposed to be 60 angle if it's triangle structure. Stressed. That's why this is unstable and sigma bond looks like pi. Take a look. Supposed to be direct overlapping, but to compensate this stress compression, it seems like this direct overlapping, Sp3 hybrid orbital overlapping, it seems like it's above the chain, above the line between two centers. So that's why it's a band bond, banana bond, and as a result for cycloalkanes different mechanism is typical. Take a look. For cyclobutane, stressful, not so high, but it's still almost 20. So that's why it still will be stressed, and that's why for compounds such nature, cycloalkanes, small cycle, cyclopropane, additional reaction, electrophilic because of sigma bond looks like pi, it's closer to be attacked. So cyclopropane, additional electrophilic, much more typical than substitutional. For cyclobutane, additional electrophilic, but somehow some percent of substitutional radical also present. But cyclopentane and others, they already hybridization Sp3, and it's not stressed 109. They are substitutional radical, same as for alkanes. One more thing for electrophilic reaction I want to tell you, and that's it. Electrophilic substitutional reaction for benzene ring. It's a reaction substitution of one of few hydrogen in a benzene ring. So here can be few types of reaction. It can be halogenation, nitration, alkylation, acylation, sulfonation also. So some of them you must know, and for benzene itself, this reaction happen quite stressful because of benzene is aromatic, and that's why we need catalyst, we need temperature and pressure. So substitutional clear, hydrogen one of few substitutes, electrophilic clear, why the benzene ring, it's a high electron density. So for today's lecture is over.